When we talk about building search engines for modern artificial intelligence applications, the conversation usually centers on one of two extremes. You either build a massive, expensive in-memory database that runs blazing fast but costs a fortune to scale, or you build a cheap system that stores everything on disk but struggles with latency. This trade-off has defined the industry for years. The assumption has always been that if you want speed, you must pay for RAM, and if you want cheap storage, you must accept slow response times. But what if that assumption is wrong? What if you could get the microsecond latency of an in-memory system while storing petabytes of data on object storage for pennies on the dollar? This is the question that drives the architecture of a new open-source project called Firn. It combines two powerful technologies, Lance and Foyer, to create a multi-tenant vector and full-text search engine that lives on Amazon S3. The goal here is not just to store data, but to solve the specific problem of data isolation in a shared environment without sacrificing performance. In a multi-tenant system, you are serving multiple different customers or applications from the same physical infrastructure. The critical requirement is that tenant A must never see tenant B's data, and the routing logic must be fast enough to handle thousands of requests per second. To understand how Firn achieves this, we first need to look at the underlying storage engine, Lance. Lance is built on top of Apache Parquet, which is a columnar storage format. This means data is stored in vertical columns rather than horizontal rows. When you query for a specific vector or a text snippet, the system only reads the columns it needs. This design allows Lance to leverage the power of cloud object storage like S3. Instead of loading entire database files into memory, Lance can stream data directly from the cloud. But streaming from S3 usually implies high latency. How does Firn bridge that gap? The answer lies in the integration with Foyer. Foyer is a tiered storage engine that introduces a sophisticated caching layer. It creates a hierarchy where the most frequently accessed data lives in RAM. The next tier is on fast local NVMe drives, and the cold data sits on S3. When a search request comes in, Foyer checks the RAM cache first. If the data is there, the response is nearly instant. If not, it checks the NVMe layer. Only if the data is not found locally does it fetch it from S3. This hybrid approach means that the system behaves like an in-memory database for hot data while maintaining the low cost of object storage for the entire dataset. Quick resource note before we go deeper, I keep a curated set of Amazon search links in the description for the kinds of desk gear, local AI hardware, storage, power, lighting, and builder tools that are perfect for engineers and builders like us. Some are affiliate links, so I may earn a commission at no extra cost to you. Please help support the channel. Use these links as a starting point if you're upgrading your own setup. Now consider the specific challenge of multi-tenancy. In many systems, the solution is to create a separate database instance for every single tenant. This provides perfect isolation, but it is a logistical nightmare. You end up managing hundreds of separate processes, each with its own overhead, leading to massive resource waste. Firn takes a different approach by using the native partitioning and versioning capabilities of Lance. Instead of separate databases, the system stores all tenant data in a single logical store but partitions it by tenant ID. This partitioning acts as a logical wall. When a request comes in, the system uses the tenant ID to route the query directly to the correct partition. The search engine never has to scan through data belonging to other tenants. This is achieved through Lance's data versioning, which allows the system to snapshot and manage different versions of the data without duplicating the entire dataset. It is like having a single library where every book is stamped with the owner's name, and the librarian knows exactly which shelf to check based on that stamp, rather than searching the entire building. The routing logic is the heart of this architecture. It must be deterministic and extremely fast. If the routing logic introduces even a millisecond of delay, the performance benefits of the caching layer are lost. The system uses the tenant identifier as a primary key for the partitioning strategy. This means that as new tenants are added, the system dynamically creates new partitions without requiring a complex migration or downtime. The data isolation is enforced at the storage level, meaning that even if the application layer has a bug, the underlying storage engine will not accidentally expose one tenant's data to another. Another critical component is the combination of vector search and full-text search. Many modern applications, especially those involving retrieval augmented generation, need to search by meaning and by keyword simultaneously. Traditionally, this required a polyglot persistence stack where you would run one database for vectors and another for text, then merge the results in your application code. This adds complexity and latency. Firn eliminates this by supporting both search types within the same Lance table. You can query for semantic similarity while also filtering by a text keyword, all in a single operation. This unified approach significantly reduces the operational overhead for developers building complex AI pipelines. The implications of this architecture are profound for the cost of running AI applications. By leveraging S3, you avoid the exponential cost growth associated with in-memory databases. You can scale from a few thousand vectors to billions without needing to buy more expensive RAM. The cost is primarily dictated by the amount of data you store and the bandwidth you consume, both of which are significantly cheaper than dedicated memory. This opens the door for startups and smaller teams to build production-grade RAG applications that were previously out of reach due to infrastructure costs. Furthermore, the use of standard formats like Parquet means that the data is not locked into a proprietary system. You can query the data using standard SQL engines like DuckDB or Polars. This flexibility allows you to perform ad hoc analysis, export data for reporting, or run batch processing jobs without needing to go through the search engine API. It creates an open lakehouse architecture where the vector search engine is just one interface to a much larger, accessible data lake. The community response to this approach has been enthusiastic because it addresses a real pain point. Developers are tired of choosing between performance and cost. They are tired of managing complex stacks that require specialized expertise to operate. By combining Lance and Foyer, Firn offers a solution that is both powerful and accessible. It demonstrates that high-performance search does not require expensive dedicated hardware or proprietary software. It can be built on top of standard, open technologies that run on any cloud provider. As we look at the future of vector databases, the trend is clearly moving toward these open lakehouse architectures. The ability to convert from standard Parquet files and use familiar SQL tools for hybrid search is becoming a primary driver over proprietary vector-only solutions. The integration of full text and vector search within a single engine is no longer a luxury. It is becoming a necessity for efficient AI applications. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.